Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. So let's get moving. Bam! So today we are talking about electrolytes and non-electrolytes. I'm assuming that you have heard the word electrolyte before. Maybe if you are playing any kind of sport or activity where you're rigorously moving, like a sport or something like that, and you've been told, well, you got to replenish your electrolytes, and you've drinking some kind of sports drink to replenish those electrolytes. Okay, so the question is, what is an electrolyte then? Why replenish those electrolytes and why add more electrolytes to you? Let's figure this out here. So in terms of chemistry, what is an electrolyte? So an electrolyte is something that conducts electricity. Okay, electrolyte. Okay, acids, bases, and salts, those are things that form ions in solution, are all examples of electrolytes. Okay, so if you remember way back to nomenclature, nomenclature says that if I have a cation and an anion that's in the California form, the cation first, the anion second, all of those cation-anion combinations are electrolytes. Okay, so that is, they have ions in solution. Okay, and then non-electrolytes. What's a non-electrolyte? A non-electrolyte does not conduct electricity. Okay, sugars are example of that. Any kind of sugar. So glucose, fructose, sucrose, all those sugars do not conduct electricity because they are non-electrolytes. In addition to that, we have alcohols. Alcohols are non-electrolytes. They typically have a carbon and a hydrogen and then a hydroxide group associated with them. Okay, those are also alcohols. Molecular substances, these are binary nonmetal compounds, so dinitrogen pentoxide, carbon dioxide, carbon monoxide, sulfur trioxide are all examples of binary nonmetal compounds, which are non-electrolytes. They do not conduct electricity in them. Pure water is also a non-electrolyte. There are no ions in solution. Well, theoretically, there's no ions in solution, but there's an equal number of hydrogen and hydroxide ions, of which their dissociation is so very small that we effectively assume that there is none. So for pure water, it is a non-electrolyte. Okay, so here's these two examples here. Okay, the one in the blue and the one in the purple as far as the circles. Okay, you should see the one in the blue in the top has plus and minus charges. The one in the bottom with the purple around it are all attached together. Okay, and you should see what's happening in solution. Okay, and what's happening in solution is that electrolytes, which are in the top picture, have ions in solution. That's either positive charges or negative charges. And non-ionic compounds, okay, which are non-electrolytes, do not have ions in solution. And one of the differences here is the Van Hoff factor. The Van Hoff factor, if you remember back from the solutions unit, if you have an I of 1, then it does not dissociate. Okay, but if you have an I that's greater than 1, then it does dissociate. So electrolytes have an I, a Van Hoff factor, that is greater than 1, and non-electrolytes have a Van Hoff factor that is equal to 1. Hopefully that brings some prior knowledge back to you. All right, so strong versus weak electrolytes. Okay, now we got electrolytes which conduct electricity and non-electrolytes which don't conduct electricity. And then there's another subcategory of the electrolytes. And so we have strong electrolytes which conduct electricity, of course, and weak electrolytes which, of course, conduct electricity as well. Okay, so they're classified, that is the difference between the strong and the weak, according to their extent of a dissociation or ionization. Okay, strong electrolytes dissociate or ionize 100%. That means they break apart 100%. Okay, all salts fit into this category. Only the strong acids dissociate 100%. Only the strong bases dissociate or ionize 100%. Weak electrolytes dissociate or ionize less than 100%. So it could be 99%. That's still less than 100%. So acids and bases that are not strong, i.e. that are weak acids and weak bases, fit within this category of a weak electrolyte. Okay, so strong, weak, and non-electrolytes, and let's give a picture, a diagrammatic picture of what this actually looks like so you can see this at the molecular level. Okay, we've got 3 containers here with 3 different solutions in them. On the far left is a strong electrolyte. In the middle is a weak electrolyte, and in the right-hand side is the non-electrolyte. These are all in solution. Okay, so on the far left with the strong electrolyte, these are 100% dissociated or 100% ionized. That means that we have ions in solution. Okay, and you notice I've pointed out 2 different ions. One that's negative, one that's positive, but they are all ions in solution. All of them are ions in solution. Okay, what fits in this category of a strong electrolyte which produces complete dissociation or complete ionization? And that is any salt, a strong acid, Sa, a strong base, an Sb. Okay, and sodium chloride is a perfect example of this. NaCl is an example of a salt that is a strong electrolyte. Okay, so these are strong conductors of electricity. So this is like a light bulb, and you put it in this solution that has been completely dissociated. It allows the electrons to complete this circuit, therefore, and therefore the light shines brightly, and it's a strong conductor. Okay, you certainly don't want to jump into a bathtub that has strong conductors, and those would be salts, strong acids, strong bases, and throw a hairdryer in there. That would be a bad thing because that would conduct electricity very well. Okay, now in the middle column here we have a weak electrolyte. And weak electrolytes dissociate or ionize less than 100%. Okay, so anything less than 100% but still ionizing. So therefore you do have ions in solution. Okay, but you also have molecules. That is a cation and an anion combination that has not dissociated. So you should see that these molecules here have not broken apart and separated. Their cation and anion are still held together. That's why we still call them a molecule, and they are not dissociated, unlike the ions that I have circled in the yellow there, which have completely separated from one another. Okay, weak acids, that's a Wa, or a weak base, that's a Wb, fall within this category of a weak electrolyte. And ammonia, that's NH3, is a perfect example of that. Or vinegar, which is an acid, which also fits as the perfect example of this, of acetic acid. Okay, all right. Now, do these conduct electricity? Well, most certainly they do, but they conduct electricity in a weak way. So the light bulb is not going to be completely lit up brightly like the strong conductor of a strong electrolyte, but the light bulb will light up, but dimly. Because there are ions in solution, it will close the circuit, but not very well. So if you have a 100-watt light bulb on the left-hand side with the strong electrolyte, that light bulb will be lit up all the way. If you have that same 100-watt light bulb in the weak conductor of the weak electrolyte, it will not light up all the way. Okay? All right, now the far right-hand column is a non-electrolyte, and these are things that do not dissociate it, and there are no ions in solution. They do not ionize, they do not dissociate. Okay? They are all entirely molecules. They are not combined in a cation-anion form. Okay? Of your nomenclature way back when. Okay, these are molecules, and molecules, an example of this is sugar. So C12H22O11. Okay, that is a sugar molecule. Okay, and these are non-conductors. So if you put that light bulb in there, it will not conduct electricity whatsoever because there are no ions in solution, and therefore the circuit cannot be closed. Okay. So this is the difference molecularly on the atomic level here that you can see between the strong conductor, a weak conductor, and a non-conductor, and that is a strong electrolyte, a weak electrolyte, and a non-electrolyte. Okay? All right. So some examples of strong and weak electrolytes are as follows. Okay, according to the extent of classification. So strong electrolytes, 100% dissociated, all salts. So these are a cation and an anion combination, but they cannot be a hydroxide or an oxide because those are going to be bases. Okay, strong acids, of which there are only 7. I don't know if you remember the diatomics, but here is a little thing to remember the diatomics. So you're going to take your right hand. You're going to take your right hand and make a little pistol out of it. So when you were, like a 3-year-old, you're playing guns. Bang, 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 bang. You're going to make a little pistol out of it. Okay, you're going to take this here, little pistol, and you're going to stick it on your forehead like Shrek. Okay, and now you have an L on your forehead. Now that you have that L on your forehead, you're going to take this L on your forehead and then turn it this way. What number do you see? You see the number 7. Okay, so how many diatomics are there? There are 7 of them. And if you take this 7 right here and place it on the periodic table, you will see that most of the diatomics form in that 7-shaped pattern that's on the periodic table. And that is nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Unfortunately, that's only 6. So the next one, the 7th one, is the hydrogen. All of those are diatomic. Okay, now there are actually 7 diatomics, and there are 7 strong acids. So that's the beautiful thing. And there's another 7 coming up here because you are having 3 7s. So there are 7 strong acids. These are the 7 strong acids. You need to memorize them, okay, so that you know which ones they are. So that's HClO4. Okay, then that is perchloric acid or hyperchloric acid. Then there's HClO3, which is chloric acid. Then there's HNO3, that is nitric acid. Then there is H2SO4, that is sulfuric acid. There's HCl, that's hydrochloric acid. There's HBr, hydrobromic acid, and HI, hydroiodic acid. So we've got 7 strong acids. All other acids are weak. Okay? Then we have the strong bases. So the strong bases are group 1 and group 2 hydroxides. Absolutely group 1, except for hydrogen, because that's water, and group 2 hydroxides. Some of the group 2 hydroxides don't fit into this category, so you want to ask your professor or your teacher exactly. Okay, but sodium hydroxide is a group 1 hydroxide that is a strong base. Calcium hydroxide is a group 2 hydroxide, and that is a strong base. Okay, weak electrolytes dissociate less than 100% or ionize less than 100%. Okay, weak acids and weak bases. What are the weak acids and weak bases? Well, they are not the strong ones. So you have to know the strong acids and strong bases to figure out what the weak ones are. So if it's an acid and it is not one of the 7 strong, it's weak. If it is a base and it is not one of the group 1 or group 2 hydroxides, it's weak. It's that simple. Okay? So if it's not strong, then it's weak. So examples of this, a weak acid would be acetic acid. This is the example that all chemistry teachers and textbooks use, is acetic acid as the weak acid. And ammonia is the example of a weak base that all chemistry textbooks, all chemistry teachers and professors use as a weak base. Okay, so here's an example of a reaction here. We've got a strong base, sodium hydroxide, plus a strong acid, hydrochloric acid, and that will produce a salt, that is sodium chloride, and HOH, which is water. There's a delta H of enthalpy, that's a change in enthalpy of negative 58 kilojoules per mole. That's letting you know that this is an exothermic reaction. Okay, this is a really cool reaction. You have a strong base, strong acid produces a salt and water. This is an acid-base neutralization reaction. Okay, if you have the same volume and the same molarity of the acid and the base, then it would be a complete neutralization, and you would get a pH of 7 at the end, and you would have just salty water at the end. All right, so here's a little bit of humor here to break up this video because I know it's getting kind of long, but that's okay. Okay, how do you tell the difference between a plumber and a chemist? Here's a plumber. Here are a number of chemists doing chemistry. Okay, ask them to pronounce unionized. So the plumber will pronounce it unionized. The chemist will pronounce it unionized. All right, hopefully you enjoyed that joke here. All right, so here is the list of the strong acids. So the acid name, their formula, and the Ka. What does the Ka? This is the acid dissociation constant. Okay, so remember the equilibrium unit, and we got KeQ values. This is going to be a Ka because it's specific for acids, therefore the A. But it's a constant of the dissociation. That's products over reactants, stoichiometric coefficients as exponents, except for specifically for acid for the Ka. So perchloric acid, HClO4, that's a very large Ka. We got hydrotic acid, that's Hi, that has a 3.2 times 10 to the 9 Ka value. Obviously, since this Ka is greater than 1, you should see that this is product favored. That's why it's a strong acid, because it dissociates 100%. Hydrobromic acid has a Ka of 1.0 times 10 to the 9. Hydrochloric acid, which is muriatic acid, so if you have a pool at home, you're purchasing muriatic acid, which is hydrochloric acid. That is also a strong acid, as a dissociation constant of 1.3 times 10 to the 6. Sulfuric acid, H2SO4, which is otherwise known in ancient ways as oil of vitriol, has 1.0 times 10 to the 3. Okay, this is the only multiprotic acid of the strong acids, and it's only the first hydrogen that disassociates to form a strong acid. After that first hydrogen comes off, then you still have that second hydrogen attached. That is not a strong acid. Nitric acid, HNO3, is aqua fortis. That is a strong fort. Okay, nitric acid has a dissociation constant of 2.4 times 10 to the 1. This is also an oxidizing acid, so it has some special abilities. It's kind of like a superpower. Okay, then there's chloric acid, that's HClO3 at 1.0 times 10 to the 1. And all these acids have Ka's greater than 1, therefore they are strong, therefore they are product favored. All other acids have Ka values that are less than 1 and therefore are weak. That's how we classify them, according to their Ka value and according to their dissociation. Okay? Negative exponents are reactant favored. Therefore, those Ka values are less than 1. Hopefully that makes sense for you. Okay? Aqua regia, that is royal water, is concentrated nitric acid and concentrated hydrochloric acid in a 1:3 ratio that is mixed fresh. And this is the only special of all the acids which will dissolve special royal metals like platinum, like my wedding ring, or gold, or silver, or even titanium. But it has to be fresh, and there is some aqua regia dissolving some gold. Super cool little bit of trivia. Okay, my last password on my computer was H3PO4, and I was told it was too weak. So I changed it to a much stronger password, HClO4. Hey, here's a list of the strong bases. So group 1, hydroxides. So lithium hydroxide, sodium hydroxide, otherwise known as lye or caustic soda. There's potassium hydroxide, which is caustic potash, rubidium hydroxide, cesium hydroxide. And here are some group 2 hydroxides. Magnesium hydroxide, calcium hydroxide, which is slaked lime or hydrated lime or even lime water, strontium hydroxide, barium hydroxide. Okay, these all have KBs because they're bases, so a KB, that are greater than 1 and are therefore strong. All the others are weak. Okay, that was hopefully a great video here for you on more acids and bases, salts, electrolytes, all kinds of great stuff there. I am the Crazy Hat Chemist. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Pass my YouTube channel on to all your friends that need to learn about chemistry. I got so much great curriculum here. Please watch all my videos. I'll see you next time for more cool chemistry videos. Bye for now.